So, good day everyone. I hope everyone is doing good right now. So, I'm EUNICE Wendy Bernales from BSIS 1B, and we are the Tribe 1, Archimedes, and we will be discussing our assigned topics. So, I will start with the variables. So, variables is a quantity which during a calculation is assumed to vary or be capable of varying in values. This is an element, feature, or factor that is liable to vary or change. And so, yung variables po is represented by a letter like X or Y or like A or B. And also, yung variables is ito yung symbol na value na hindi pa natin alam. So, the advantage of using variables. So, it allows you to give a temporary name to what you are seeking so that you can perform concrete computation with it to help discover possible values. So, it is a symbol for a number where the value is unknown. So, typically, we use a letter. Kagaya po ng sinabi ko kanina, we use a letter to represent a variable. For example, x plus 5 is equals to 10. So, the x is the variable. And to illustrate the second use of variable, consider the statement. So, no matter what number might be chosen, if it's greater than 2, then its square is greater than 4. In writing sentences using variables. So, in writing sentences using variables, every word matters. So, wrong interpretation for the words may lead to wrong representation. For example, are there numbers A and B with the property that? So, that a phrase in a A squared plus B squared is equals to A plus B squared represented in variables. So, another example, given any number, its square na negative. So, the solution for that situation is for any real number R squared is greater than for equal to 0. And lastly, for all the real number R squared is greater than or equal to 0. So, the next one. So, there are three most important kinds of statement in mathematics. So, the first one is the universal statement. So, universal statements, it is a state that a certain property is true for all elements in a set. Like for example, all positive numbers are greater than 0. So, the second statement is the conditional statement. It says that if one thing is true, then some other thing also has to be true. For example, if 378 is divisible by 18, then 378 is divisible by 6. So, another situation is that if it rains, then they cancel school. So, those are examples about conditional statement. And the last statement is the existential. It says that there is at least one thing for which the property is true. Like for example, there is a prime that is even, that number. So that number is 2.
next lesson is universal conditional statement. Important facts about universal conditional statement is that they can be rewritten in ways that make them appear to be purely universal or purely conditional. For example, the previous statement that can be rewritten in a way that makes its conditional nature explicit but its universal nature implicit. Let's say, for example, if A is a dog, then A is a mammal. Or if an animal is a dog, then the animal is a mammal. In this statement, we're going to write our general form into if-then form. So, by definition, conditional statements are by joining two statements, P and Q. Using words if plus then P statement is called the hypothesis and Q statement is called the conclusion. So, we have here the hypothesis and the conclusions. P is called the hypothesis. Q is the conclusion. Now, what's the difference between hypothesis and the conclusions? Hypothesis tells whether the statement is proven to be true or false, where conclusion is an evaluation of the underlying theory or data that hypothesis. Let's then a series of examples for further understand the conditional statement. Example are number 1. Now we are going to rewrite the conditional statement on each statement. Number 1, let's say for example, Filipinos are hospitable. So here are hypotheses here. Filipinos is hypothesis. Then hospitable is the conclusions. If you are a Filipino, then you are a hospitable. So in some cases, you can also write this one using a name of a certain person. Let's say for example, if Pablo is a Filipino, then he is hospitable. That's the example on how to rewrite the conditional statement. Rewriting universal conditional statement example by numbers. Let's say for example, all real number x. If x is non-zero, then x squared is positive. Letter A, if a real number is non-zero, then its square is positive. Letter B, for all non-zero real number x, x squared is positive. Letter C, if x is a non-zero real number, then x squared is positive. Letter D, the square of any non-zero real number is positive. E, all non-zero numbers have positive square or squares that are positive. That's the example of rewriting a universal conditional statement.
Universal existential statement. A statement that is universal because its first part say that a certain property is true for all objects of a given type, and it is existential because its second part asserts the existence of something. So in my own understanding, the universal existential statement is a certain property that has a real true for all objects of a given type. In addition, on what I read is that universal existential is additive inverse, which particularly talks that is first part of a property. Furthermore, I think it is connected to the law or rules of exponent. For example, every real number has an additive inverse, or for all real numbers R, there is an additive inverse for R, or for all numbers R, there is a real number S, such that S is an additive inverse for variables. Mathematics gives you the ability for refer to quantities unambiguously through that a lengthy mathematical argument. Rewriting a universal existential statement. Example, every pot has a lid. A, all pots has lid. B, for all pots P, there is a lid for P. C, for all pots P, there is a lead for L such that L is a lead for P. Existential universal statement. A statement that is existential because its first part asserts that a certain object satisfies a certain property for all things of a certain kind.
Existential universal statement. A statement that is existential because its first part asserts that a certain object exists and is universal because its second part says that the object satisfies a certain property for all things of a certain kind. Existential statement says that something exists or is true for certain elements. Universal statement says that a concept is true for a set of elements for collection of things, for example, number. For example, there is a positive integer that is less than or equal to every positive integer. Kung mapapansin niyo po, ang keyword na there is, which is a keyword for existential statement sa first part, and keyword na every, which is keyword for universal statement sa second part. Or there is a positive integer in that is less than or equal to every positive integer. Example ng positive integer is 1. Ang 1 ay mas mababa sa iba pang positive integer. Or there is a positive integer m such that every positive integer is greater than or equal to m. Keyword in a sentence gives any, for all, or every. Or there is a positive integer m with the property that for all positive integer n, m less than n. Rewriting an existential universal statement. Example, there is a person in my class who is at least as old as every person in my class. A. Same person in my class is at least as old as every person in my class. B. There is a person P in my class such that P is at least as old as every person in my class. C. There is a person P in my class with the property that for every person Q in my class, P is at least as old as Q. Kahit rewrite siya, yung thought na andyan pa din at retain pa rin yung existential universal statement. Some of the most important mathematical concepts, such as the definition of limit of sequence, can only be defined using phrases that are universal, existential, and conditional, and they require the use of all three phrases for all there is and if then. For all universal, there is existential. If then, conditional. For example, there For example, if A1, A2, A3 is sequence of real numbers saying that the limit of an approach infinity is L, means that for all positive real number epsilon, there is an integer n such that for all integer n, if n greater than n, then negative epsilon less than an, negative L less than positive epsilon.
Language of set. The word set, a formal mathematical term, was introduced in 1879 by George Cantor, 1845 to 1918. In mathematical and logic, any collection of objects or elements which may be mathematical or not. The initiative idea of a set is probably even older than that of number. Notation. If S is a set, notation X is an element of S means that X is an element of S. The notation X is an element of S means that X is not an element of S. A set may specify using the set roster notation by writing all of its elements between braces. The axiom of an extension. Say that a set is completely determined by what its elements are, not the order in which they might be listed, or the fact that some element might be listed more than once. Using the set roster notation. Example 1. A. Let A is equal open of braces 1, 2, 3, close of braces. B is equal open of braces 3, 1, 2, close of braces. And C is equal open of braces 1, 1, 2, 3, 3, close of braces. What are the elements of A, B, and C? How are A, B, and C related? B is open braces 0, closes braces is equal 0. C. How many elements are in the set? Open braces 1, open braces 1, closes braces. D. For each non-negative integers n, let union sub n is equal open braces n, negative n, closes braces. Find union sub 1, union sub 2, and union sub 0.
Solution. A, B, and C have exactly the same three elements. 1, 2, and 3. Therefore, A, B, and C are simplified different way to represent the same set. B is a set of 0 is not equal 0 because is a set of 0 is a set with one element, namely 0, whereas 0 is just the symbol that represents number 0. C, the set is a set 1 to 1, how two elements 1 and the whole only element is 1. D, U sub 1 is equals of is a set of 1, negative 1. U sub 2 is a set of 2, negative 2. U sub 0 is a set of 0, negative 0 is equals to 0 to 0. And U sub 0. Certain set of number are so frequently referred to that they are give special symbolic name. They are summarized in the table below. Symbol R is a set of all real numbers. J is a set of all integers. Q is a set of rational number of quantities of integer. Additional of superscript plus, negative, or the letters non-neg indicates that only the positive or negative non-negative elements of the set respectively are to be included. Thus, plus denotes the set of positive real numbers, and Z non-neg refers to the set of non-negative integers 0, 1, 2, 3, 4, and the fourth some authors refers to the set of non-negative integers as the set of natural number, and donate it is, and other authors call only the positive integers natural number.
Set of real numbers is usually pictured as all the points on a line as shown below. The number 0 corresponds to a middle point called the origin. So, as you can see in the picture below, set of real numbers is usually the point on a line so that every integer is a real number because the integers are all separated from each other. Real number line. Real number line is called continuous because it is imagined to have no holes. As you can see at the real number line in the previous slide, both ends have an arrow on it. That is why it's called continuous line. The set of integers correspond to a collection of points located at fixed intervals along the real number line, means that every integer is a real number because the integers are separated from each other. Set of integers is called discrete. Discrete mathematics comes from the distinction between continuous and discrete mathematical objects. Another way to specify a set uses is called the set builder notation. Let S denote a set and let P of X be a property that elements of S may or may not satisfy. We may define a new set to be the set of all elements X in S such that P of X is true. We denote this set as follows. Using the set builder notation, given the denotes the set of all real numbers Z, the set of all integers, and Z plus the set of all positive integers. Describe each of the following set.
F, A, and B are set, then A is called subset of B. Write A subset B is and only if every element of A is also an element of B. Symbolically, A subset B means that for all elements X, F, X element, A then X element B, the pairs A is contained in a B and B contain A are alternative ways of saying that A is a subset of B. Proper subset. Let A and B be a set. A is proper subset of B. F and only if every element of B is in B, but there is at least one element of B that is not in A. Proper subset. Sample. Let A equals G plus B equals n elements such that O 0 less than n less than 1 and C element 100, 200, 300, 400, 500. Evaluate the true and false of each of the following statement. B subset A. C is a proper subset of A. C and B have at least one element in common. C subset B, C subset C. Distinction between element and subset. Which of the following are true statement? 2 element 1, 2, 3. 2 element 1, 2, 3. 2 subset 1, 2, 3. 2 subset 1, 2, 3. 2 subset 1 and 2. 2 element 1 and 2.
Cartesian products. In the late 19th century, the George Cantor's began to be possible to put mathematics on a firm, logical, foundation by developing all of the various branches from the set theory and logical alone. In this theory, the major stumbling block was on how to use set to define an order pair because the definition of the set unaffected by the order in which its elements are listed. Cartesian products. For example, AB and BA represent the same set, whereas an order pair, we want to be able to indicate which element comes first. It's say that an order pair is a set the form A, AB. This set has element A and AB. If A and B, then the two sets are distinct and A is both set, whereas B, if A equal B, then we can simply say that is a both first and the second element of the first pair. In this case, the set that define the order pair become AA, which equal A. Another example of Cartesian product. For example, if A equal 1, 2 and B equal 3, 4, 5, then the Cartesian product of A and B is 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5. Order pair. Given element A and B, the symbol AB denotes the order pair consisting of A and B together with the specification of A is the first element of the pair and B if A equals C and B equals D. Symbolically, AB equals CB means that A equals C and B equals D. Order pairs. Example, A is 1, 2 equals 2, 1. B is 3, 5 over 10 equals 9 divide 1 over 2. See what is the first element of 1, 1. A, no, because the given for the letter A is not a cirtation because cirtation is represent the same set, whereas in an order pair. B, yes, because the given for the letter B is an example of cirtation. C, the first letter of 1, 1 is 1 based on cirtation lesson or example.
Cartesian product. Given set A and B, the Cartesian product of A and B, denoted, read A across B, is the set of all ordered pairs A and B, where A is in A and B is in B. Example, let A is equal to 1, 2, 3, and B is equal to U and V. A. Find A across B. We can find A across B using the values of A and B. By substitute the A across B is equal to elements of 1 and U, the elements of 2 and U, and the elements of 3 and U. And another is elements of 1 and V, the elements of 2 and V, the elements of 3 and V. That is the elements of A across B. B. Find B across A. V across A is equal the element of U and 1, the element of 6 and 2, the elements of U and 3, the elements of V and 1, the elements of V and 2, the elements of V and 3. C. Find B across B. B across B is equal to the elements of U and U, the elements of U and V, the elements of V and U, and the elements of V and V. D. How many elements are in A across B, B across A, and B is across B? A across B has 6 elements. B across A has 6 elements, and V and B has only 4 elements. The term Cartesian plane is often used to refer to a plane with the this coordinate system. We can use the Cartesian plane to plot the value of B and B.
The language of relation and function. The object of mathematics may be related in various ways. A set A may be said to be related to a set B if set A is a subset to B, or if A is not a subset of B, or if A and B have at least one element in common. A number x may be said to be related to a number y if x is greater than y, or if x is a factor of y, or if x squared plus y squared equals 1. Two identifiers in a computer program may be said to be related if they have the same first 8 characters, or if the same memory located is used to store their values when the program is executed, and the list could go on. Relation. Relation can be thought as of the totality of ordered pairs whose elements are related by the given condition. The formal mathematical definition of relation was introduced by an American mathematician and logician, C.S. Peirce, in the 19th century. C.S. Peirce, also known as Charles Sanders Peirce, was an American philosopher, logician, mathematician, and a scientist who is sometimes known as the father of pragmatism. He was known as a somewhat unusual character. Let A and B be sets. A relation R from A to B is a subset of A cross B. Given an ordered pair XY and A cross B, X is related to Y by R, written XRY, if and only if XY is in R. The set A is called the domain of R, and the set B is called its codomain. The notation for our relation R is written XRY, means that XY is the element of R.
A relation as a subset. A relation as a subset, or more formally, a relation is defined as a subset of A cross B. The domain of a relation is the set of elements in A that appear in the first coordinate of some ordered pairs, and the image or range is a set of elements in B that appear in the second coordinate of some ordered pairs. If A and B are two non-empty sets, then the relation R from A to B is a subset of A cross B. If set AB elements are, then we write a big letter R, small letter B, and this read as A related to B. In mathematics, a set A is a subset of a set B. If all elements of A are also elements of B, B is then a superset of A. It is possible for A and B to be equal. If they are unequal, then A is a proper subset of B. The relation of one set being a subset of another is called inclusion, or sometimes containment. A is a subset of B may also be expressed as B includes or contains A, or A is included or contained in B. The subset relation defines a partial order on sets. In fact, the subset of a given set from a Boolean algebra under the subset relation, in which the join and met are given by intersection and union, and the subset relation itself is the Boolean inclusion relation. The circle relation. The circle relation can be defined as the locus of all points that satisfy the equation x squared plus y squared equals r squared, where x and y are the coordinates of each point and r is the radius of the circle. The equation has three variables, x, y, and r. If we know any two, then we can find the third. So if we are given a point with known x and y coordinates, we can arrange the equation to solve for r.
B. What are the domain and codomain of C? The answer is the domain and the codomain C are both R. The set of real numbers. C. Draw a graph for C by plotting the points of C in the Cartesian plane. X squared plus y squared equals 1. So, 1 is the answer, kaya kukunin na lang yung negative 1 sa y-axis. And equal yung sagot nila, kaya makakabuo ng circle. Arrow diagram of relation. Let A equal set 1, 2, 3 and B equal set 1, 3, 5, and define relation S and T from A to B as follows. For all x, y element A cross B, x, y element S mean that x less than y is a less than relation. T equals set 2, 1 and 2, 5. Draw arrow diagram for S and T. First example on the left side is 1, 2, 3A and 1, 3, 5B. And the right side 1, 2, 3A and 1, 3, 5B. Function. Function is defined in a way that depends only on the concept of set. Function is a relation from a set of inputs to set for possible output where each input related to exactly one output. Function. A function f from a set A to a set B is a relation with domain A and codomain B that satisfies the following two properties. 1. For every element x and A, there is an element y in B, such that x and y is element to f. 2. For element x and A and y and z in B, if x and y is element of f and x and z is element of f, then y is equal to z. Notation. If A and B are set and if is a function from A to B, then given in any element x and A, the unique element in B that is related to x and by f denote f of x, which is read f of x.
Function and relation on finite sets. Example, let A is equal to set 2, 4, 6, and B is equal to 1, 3, 5. Which of the relation R, S, and T defined below are function from A to B? Letter A, R is equal to the set 2, 5, 4, 1, 4, 3, and 6, 5. Yung 4 po, kung makikita po natin sa set ng R, may kapareho po, yung dun sa ordered pair, may kapareho po yung 4. And it's not, it doesn't satisfy the property 1 ng function. Kung alam nyo na po yun, ay letter B, for all xy is an element of A cross B. Xy is an element of S, means that y is equal to x plus 1. So, S is not a function. Dito naman po, kung makikita po natin, yung value ng A, yung 2, 4, 6, isa-substitute lang po natin siya sa value ng x dun po sa equation na y is equal to x plus 1. And then, kung makikita po natin, kapag sinubstitute po natin yung 2 sa x, magiging yung y is equals to 3. And makikita po natin yung 3 sa set ng letter B. And then, yung kapag yung 4 naman po ang sinubstitute natin sa x, ang y is equal to 5. And makikita din po natin yon sa set ng B. Pero, kapag sinubstitute nyo po yung 6 sa x, ang y is equal to 7 na po and wala na po siya sa set ng B. Kaya po, S is not a function. Letter C, T is defined by the arrow diagram and T is a function kasi sa value ng x, wala po siyang naulit na value. Makagawa tayo ng ordered pair na 2, 5, 4, 1, and 6, 1. Okay lang po yun na na-value yung value ng y, basta po walang maulit na value ng x. Kaya T as a function. Equality of a function. If f and g are functions from a set A to a set B, then f is equal to the set xy is an element of A cross B
and y is equals to f of x, and g is equal to xy is an element of A cross B, and y is equal to g of x. It follows that f equals g, written f is equal to g, if and only if f of x is equal to g of x for all x in A.